Hello there. All right, we are going to review Riemann sums in this video. And to remind you what a Riemann sum is, we're using different shapes, often rectangles, sometimes trapezoids, triangles, to find areas underneath curves, okay? And again, that curve is going to have been a derivative graph or a velocity function, if you will. And when we're finding the area under that curve, we're finding a quantity or an amount over the time period that they gave us. So in this first example, they said that the rate at which material is deposited at a recycling center is modeled by function R, and R is measured in tons per hour. So again, that's a rate. T is the number of hours since the center opened. Using a trapezoidal sum with 3 subintervals indicated by the data in the table, what is the approximate number of tons of material deposited in the first 9 hours since the center opened? Notice that 9 hours is our total time difference, so we're going to use all of our information given in the table. A trapezoidal sum will be the area of trapezoids, and as a reminder, that's just like the area of a triangle, but instead of one base we have 2. So it's 1/2 bases times height, or 1/2 my height times the sum of the bases. Okay, when we're making 3 trapezoids with this data, these changes in the time are actually the heights of your trapezoid. So I'm going to factor out a 1/2. My height of the first trapezoid would be 2, and his bases are the values of the function 15 and 9. So I'm going to say 15 plus 9. My second trapezoid has a height of 5, which is the distance from 2 to 7, and then bases of 9 and 5. And my last trapezoid has a height of 2 and bases of 5 and 4. This is a multiple choice, non-calculator question. So when we add these up, we would have 1/2 of 15 plus 9 is 24. 2 times 24 is 48. 9 plus 5 is 14. 14 times 5 is 70. And 5 plus 4 is 9 times 2 is 18. When we add that all together and take half of it, we get 68. So again, that is the number of, what are we talking about again? Number of tons of recycled items that are being deposited during the first 9 hours that the center is opened. Okay, as we look at the next example, again, they gave us a table and they want us to make a left Riemann sum to approximate, again, this is just fancy for the area under the curve or the amount, using the subintervals given. And again, those subintervals are saying from 0 to 25, that's a base, from 25 to 30, that's another base, and from 30 to 50, that's another base. A left Riemann sum is referring to a rectangle. The area of a rectangle is base times height. If we're dealing with our first base, the distance from 0 to 25 is 25. The left height, the left value of my function there is 4. The next base of my triangle would be the distance from 25 to 30, which is 5, and the left height being 6. And my final base is the distance from 30 to 50, which is 20, with a left height of 8. When we multiply 25 times 4, we obviously get 100. 6 times 5, we're at 30. 20 times 8, we're at 160. Add that all together, and we're at 290. Just a reminder, with left Riemann sums, you will never use the right-hand height or right-hand value of the function. Okie doke. Number 12, let f be the function given by 9 to the x if 4 subintervals of equal length are used. What is the value of the right Riemann sum approximating the area from 0 to 2. So again, my base, I'm trying to go from 0 to 2, and I need 4 subintervals. So in order to cut that evenly, 2 subintervals would have bases of 1, but 4 subintervals will have bases of 1/2. Okay, in order to find out what a right Riemann sum is, we've got to do base times height. Again, my bases are all going to be 1/2, so I'm going to factor that out. I need 4 heights here. And the height is just the value of the function at those right base x values. So at the right x base values, so if I were to draw what a right Riemann sum looks like of an exponentially increasing function, a right Riemann sum would be an overestimate. And again, I'm going to plug in my base values into my function. My function was 9 to the x, but when I look at my base values, and they are 0, 0.5, 1, 1.5, and 2, when I'm using a right Riemann sum, I'm not going to use the left-hand base value, the left-hand x value. So when I'm plugging in my x values into my function, I need to make sure I use the right base value, which in the first case will be 1/2. So I've got 9 to the 1/2. I've got 9 to the next base value, which is 1, plus 9 to the next base value, which is 1.5. I'm going to say that is 3/2. And 9 to the farthest right-hand base value, because again, I'm doing a right Riemann sum, I will not use the leftmost height. And you get those heights by plugging in the x value into the function. This could be a little daunting looking, but then we say, okay, I remember that 9 to the 1/2 is the same as the square root of 9. The square root of 9 is 3. 9 to the first is 9. 9 to the 3/2 is the same as 9 to the third power square rooted. But I do not know offhand what 9 to the third power is, so do the square root first. We know the square root of 9 is 3. 3 to the third power is 27, much more manageable. 9 squared is 81. When we add things together, I'm going to think of this as 27 plus 3 is 30. 81 plus 9 is 90, getting me 90 plus 30 is 120, and half of that is 60. All right, let's keep cranking.